So this slide's titled Enthalpy Part 1. You're going to find enthalpy is just a fancy word for heat. So heat is a form of energy. And usually energy is left to the physicists, right? Chemists study matter. Physicists study things that aren't matter, like heat and energy and electricity and all that stuff. But there is definitely overlap. So, obviously chemical reactions can be used to produce heat, and we can use heat to make a non-spontaneous, non-desirable reaction occur. So heat is both a byproduct and sometimes a reactant of chemical reactions. So that's why we have a whole chapter on this, where heat might seem like a physics topic. We do have to cover it in chemistry, and if you take Chem 102, we cover it in even more detail. We have to cover it in chemistry because a lot of chemical reactions produce heat; those are exothermic reactions, and a lot of chemical reactions absorb heat; those are endothermic reactions. So, getting a little ahead of ourselves, the energy of a chemical system can change via two ways. So, the change of energy in a chemical system can change through heat or work. And yes, we use a lowercase q as an abbreviation for heat. Why is that? Don't ask me, right? Capital H is enthalpy, which is like heat. And in fact, if pressure is constant, it is heat. So the H is kind of already taken, so maybe that's why they went with the Q. I really don't know why we use a Q, but we use a lowercase q for heat, and we use a lowercase w for work. So the internal energy of a system can change by having work done to a system or the system doing work, or by adding heat to a system or the system releasing heat. The hardest thing about this is a very easy equation, right? The change in energy is equal to the amount of heat and the amount of work, right? The hardest thing about this equation is assigning the values as positive or negative values of Q or W. So how do we do that? If the system is doing work or releasing heat, then we assign it as a negative value. So negative values are when the system is doing something. But if we are doing work to the system, or we are putting heat into the system from the environment, then we assign that a positive value. So that is the trickiest thing. Now we do have special words. A negative Q is an exothermic reaction, and a positive Q is an endothermic reaction. So let me kind of give some examples here. Let's hop up onto the whiteboard, and we'll talk about some examples of this. Oh, come on now, chair. So chair. There we go. So first, let's talk about work, because we're not all physicists, right? So work is equal to a force times a distance. You don't need to know that unless you're taking physics, then you need to know that. Okay, so work is a force times a distance. But we're going to use this to talk about how a system could do work or have work done to it. So let's imagine we have a gaseous system in like a piston. Okay. So we got a gaseous system in this cylinder, maybe like in an internal combustion engine. What positive work would look like would be if we apply an outside force across the distance to this piston, to this gaseous system. So here's our system. So if I apply force over a distance to this gaseous system and I compress it, I have now given this system more stored up chemical potential energy, right? Because it's now at a higher pressure, right? So that's why we assign this as a positive work, right? The system gained energy by having work done to it. So it gained energy via that mechanism. What negative work would look like is if we had like a spark plug down here and we ignited this gas, it goes boom. Now the system, when it explodes, applies a force over a distance to the surroundings, right? The system is doing the work, and we would assign that a negative W value. So it's kind of hard to figure like what are they talking about here with these positive and negatives, right? Until you actually kind of look at it, think about it until we talk about what work is and is a force across a distance. Heat is pretty easy. If we add heat to the system, if we take our gaseous system and we burn a flame, we put a flame underneath it and we heat it up, that system is gaining heat from the environment. That's a positive Q value. That would be endothermic. And if we would say take the system and put it in an ice water bath, now the system would be releasing heat to the environment. That would be a negative Q. Okay, so which way is heat going in or out? If heat is going in, it's a positive Q. If heat is going out, it's a negative Q. So let's try these two. Why don't you give these a shot? What is the change in energy per system that is being heated by 31 kilojoules and doing 13 kilojoules of work? And then what is the change in energy per system that is giving off 5 kilojoules of heat and having 25 kilojoules of work done to it? Go ahead and give it a shot. All right, so if we look at the top one, it's being heated by 31 kilojoules and doing 13 kilojoules of work. So it's being heated, it's gaining heat, so that's a positive 31 kilojoules for Q. And it's doing 13 kilojoules of work, that's a negative 13 kilojoules for the W. So the change in energy is equal to Q plus W, so that's 31 kilojoules plus a negative or minus 13 kilojoules. What do we got there? The 31 minus 13, 18 kilojoules of energy. So at the end of the day, even though the system is emitting some thermal energy, some heat, it's gaining more energy by the work that's being done to it. So the system is gaining energy overall. It's a positive 18 kilojoules of energy that the system is gaining. So even though it's releasing heat, okay, it's having so much work done to it that it cancels it out and even adds to it. So it's actually gaining energy. So this next one, what is the change in energy per system that is giving off 5 kilojoules of heat? So now we have a Q that is a negative 5 kilojoules. And it's having 25 kilojoules of work done to it. So now the work is a positive 25 kilojoules. So here we go. The change in energy is equal to negative 5 kilojoules plus 25 kilojoules. That's a positive 20 with a decimal point, technically, with the sig figs, ones place, as we're adding or subtracting. This again, the system is gaining 20 kilojoules of energy just from, it's having more work done to it than it's losing through heat. I actually misspoke on this past one. This system was being heated and doing work. It's losing energy by doing work, and it's gaining energy by being heated. I had those reversed. I was looking at them backwards. But in this system, it's giving off thermal energy, having work done to it. It's having more work done to it than it's losing through heat. So that's a positive 20 kilojoules. So positive 18, positive 20. Hopefully you're able to assign the positives and negatives. Just think about, is the system doing it, or is it being done to the system? If the system's doing it, put a negative. If it's being done to the system, put a positive. Cool. All right, how do we measure energy? Energy is measured in two main units, the calorie and the joule. Now, you are probably familiar with the calorie and because of food calories. A food calorie is actually 1,000 scientific calories. If you ever look on the back of a nutrition label, they actually capitalize the C. And in fact, I have a LaCroix, which has 0 calories, but they capitalize the C in calories. And that actually is what makes it a kilocalorie. So not very good science there. Okay. So if you're on like a 2,000 calorie diet, you're actually on a 2 million calorie diet. You're actually on a 2,000 kilocalorie diet, which is a 2 million calorie diet. So it sounds a little better that way, right? Until you realize that jelly beans like 450 calories. If you actually measure it in scientific calories. Ooh, something in the chat. Cool, Elliot. I hope you get that figured out, man. I don't know what's going on. All right. So here's the other way to measure energy, and that's the joule. Okay, and you can convert between calories and joules. Maybe you want to write this down. A calorie is equal to 4.184 joules. 4.184 joules. What is a calorie? Well, a calorie, a little c calories, I'm talking scientific calorie, not a food calorie. A scientific calorie is the amount of energy needed to raise 1 gram of water 1 degree Celsius. So to take a milliliter of water and raise it 1 degree Celsius, that's what a calorie is. You can imagine a calorie is not a lot of energy. You can rub your fingers together and release enough energy to warm a milliliter of water by 1 degree Celsius, right? You can easily release enough. A food calorie, if you're interested, a capital C calorie, that would be the amount of energy needed to raise a liter of water or 1,000 grams of water 1 degree Celsius. Um, and now we're talking, right? You know, like a food calorie is actually a decent amount of energy. If you ever saw Super Size Me, and I saw that guy died recently. In that movie, there's a scene. I remember taking my wife to see that when we were dating. Great date night movie. But there's a scene in that movie where he goes up to people in the street and asks them, "Hey, what's a calorie?" And nobody knows. And I leaned over to my wife and I said, "It's the amount of energy you need to raise a liter of water 1 degree Celsius." And she said, "Shut up! I'm trying to watch the movie." She was not impressed. So there you go, science. You know, it doesn't impress the ladies. But now you know. So next time you watch Super Size Me, you know, you can impress somebody with your knowledge of what that is. So, you know, the joule, I'm going to leave that to your physics teacher to explain what a joule is. A joule is actually a more complex unit. It's a kilogram times meter squared per second squared. It's a Newton meter, and a Newton is a kilogram times meter per second squared. So kilogram times meter per second squared times a meter is a kilogram times meter squared per second squared. And that's usually where people glaze over in physics. So I'll leave that to your physics teacher. You don't really need to worry about that, but you might have to convert between calories and joules on a worksheet or something. Cool. Okay, enthalpy, a word that freaks a lot of people out. Enthalpy, abbreviated with a capital H. Let's go back. Enthalpy, abbreviated with a capital H, is just a fancy word for heat. If pressure is held constant, enthalpy is just heat. So if we talk about the change in enthalpy, the delta H for a reaction, as long as pressure is held constant, it's just heat. Now, in Chem 101, we are going to be holding pressure constant. So whenever you hear the word enthalpy, just think heat. Okay. If heat is not, I'm sorry, if pressure is not held constant, then enthalpy, as far as I understand it, has no physical meaning. Now, if you are having trouble sleeping tonight, right, which after 3 hours of Chem 101 lecture is probably not going to be a problem. But if you're having trouble sleeping, right, Google or Wikipedia enthalpy, start reading about enthalpy. You will be out by the second paragraph. I guarantee it, right? Okay. I don't even, you know, I got a degree in physical science, I got a master's degree in physical science. Some of the stuff they talk about, I don't know. And I teach physics, you know, for part of the year. So yeah, just listen, in chemistry, especially Chem 101, when you hear the word enthalpy, just think of heat. Okay, just think of heat. It's just a fancy word for heat, all right? Thermal energy, and we are going to be just fine. So, what we can do is we can report the enthalpy or the change in heat for chemical reactions. And we usually do it like this. So if we look at this synthesis reaction, this reaction is a change in enthalpy of a positive 180 kilojoules, right? Now, what they don't write is per mole. We're going to talk about per mole of what, but it is pretty much convention to leave that per mole off of there. Okay, so it's 180 kilojoules per mole. We'll talk about mole of what here in a second. So here's what this means. Since this has a positive 180 kilojoules, that means this reaction requires heat. If it was a negative 180, then it would be releasing 180 kilojoules of energy, right? But since it's a positive 180, we're going to be adding heat to this chemical system. So we'd be adding heat here, okay, to this system. If it was a negative 180, heat would be a product, and we would put that on the product side. Let's see here. What else? What is this per mole of? Well, what it is it's per mole of reaction. Now, this can be a little confusing, so I need you to pay attention here. What that means is that this reaction requires 180 kilojoules of energy, for every mole of N2, because that's got a 1, for every mole of O2, because that's got a 1 in the balanced chemical reaction, and for every 2 moles of NO that are produced. So if I want to use up a mole of N2, use up a mole of O2, and generate 2 moles of NO, then this reaction would require 180 kilojoules of energy to be put in, and then I could produce that. Now, if I want to, take a look here, what if I only want to make 1 mole of NO? Well, this reaction right now is set up to make 2 moles of NO. So what if I only want to make half of that, 1 mole of NO? Well, then that would be 90 kilojoules of energy, right? Now, you could set this up using dimensional analysis. Here's how that would work. You could set it up like this. You could do 1 mole of NO, put that over 1, and then we could multiply this by the 180 kilojoules, but that would be per 2 moles of NO, because there's 2 moles of NO in the reaction, and you can see how we would get our 90 kilojoules of energy back out of this, 90 kilojoules. Cool. Let's take a look at another one. Let's make this a little more difficult now, though. Instead of moles, let's start in grams. So what if I want to figure out how much energy is going to be needed to make 42 grams of NO? So let's hop up to the board to do this one. Give me 1 second. I'll start writing some stuff down. Here's how I would set this up. So what we need to do is, because this is in kilojoules per mole of reaction, what we need to do is get this 42 grams of NO into moles of NO. Okay, so the first thing to do is 42 grams of NO. Pop that over 1. And we're going to divide by the molar mass of NO. So that's 14.01 plus 16. That's 30.01 grams of NO. And now we could do the same thing. Now you could break this up into 2 steps, or you could do what we just did. Let me show you the 2-step method. Maybe this will make more sense to you. There are 2 moles of NO in 1 mole of the reaction, and then it's 180 kilojoules per 1 mole of the reaction. Some people like to break it up like that. Some people just like to put that 180 over 2. It's totally up to you, however you want to do it. So here we go. 42 divided by 30.01 divided by 2 times 180. That's 2 sig figs. So 126 becomes 130 kilojoules of energy. So if you needed to make, let's say you're a chemist, your boss comes to you and says, hey, I need you to make me 42 grams of NO. Well, you know that you're going to have to put in 130 kilojoules of energy to make that happen, because this reaction is endothermic. And we were just able to figure out that that would require an input of 130 kilojoules of energy to be able to make that 42 grams of NO. Any questions on that? That can be a little tricky, right? Because now we're doing stoic with this new concept, and this is weird because it's per mole of reaction. Okay, it's a weird thing. They don't even write that. Okay, cool. Yeah, and it should just be 2 sig figs, 130. All right, man, we're about to get into Hess's law here. Woo! Yeah, love me some Hess's law. All right, I tell you what, instead of us even looking at this slide, we're gonna talk about it right now. Hess's law is kind of like a game. It's like a puzzle that only has 2 rules. So you say, well, how hard can these puzzles be if there's only 2 things you can do? And the answer is, they can get kind of tough because there's fractions and stuff involved. But let me show you the 2 rules. Here's the first thing that Hess's law says you can do with a reaction. First thing Hess's law says is, if I know the enthalpy or change in heat for a reaction, then I also know the change in enthalpy for the reverse reaction, because if I flip the reaction around, if I make the products the reactants and I make the reactants the products, then the enthalpy just takes on the opposite sign. If this requires 180 kilojoules per mole of reaction, then because of the law of conservation of energy, then if I do the opposite, if I rip this back apart, it has to release that 180 kilojoules per mole. So the first thing you can do to a reaction is you can flip the reaction around, make the products the reactants the products, and then you just flip the sign of the enthalpy. Now you'll see why you would want to do this here in a moment. Okay, eventually you'll see why we would want to do this. But this is the first thing we can do. You can flip any reaction you want because of the law of conservation of energy. Energy is not created or destroyed. If this reaction required 180 kilojoules, then running it in reverse has to release that same 180 kilojoules. That's the first rule. Okay. What's the second rule? The second rule is this. The second rule is you can multiply or divide a reaction by any number. So I can distribute any coefficient I want or pull any coefficient I want out as long as you do the same thing to the enthalpy. So for example, and again, you'll see why you might want to do this here momentarily, but what if I want to distribute a 2 into this reaction? So what if I want to multiply everything by 2? So like in math class, I want to distribute. And what if I need 2 N2s to react with 2 O2s to make 4 NOs? What if I need that reaction to happen? Well, then I need to, whatever I did to this reaction, which I multiplied by 2, I now need to do that to the enthalpy. I would need to multiply that by 2, so that'd be 360 kilojoules per mole of reaction. So if I'm multiplying everything by 2, then I need to also multiply the enthalpy by 2 as well. You can factor numbers out and get down to fractions, right? This can get a little confusing. People tend not to like this. So you don't have to obey the laws of balancing chemical equations when you're doing these Hess's law problems. For example, let's say that I only wanted to make 1 NO. So what if we divided everything by 2? Well, then that would become 1/2 N2 plus 1/2 O2 goes to 1 NO. I just divided everything by 2. Hess's law says you are allowed to do that as long as you also divide the enthalpy by 2. That would have a change in enthalpy of 90 kilojoules per mole of reaction. So you can multiply or divide by any number, distribute any coefficient you want, as long as you do the same thing to the enthalpy. So you got your 2 rules for Hess's law now. If we flip a reaction, we change the sign. And if we distribute, multiply or divide by some coefficient, then we also need to multiply or divide the enthalpy by that same coefficient. Awesome. So let's take a look here. This is exactly what we just talked about here, folks, right? Flipping a sign, distributing, exactly what we just talked about. Let's try a Hess's law problem. I'm going to copy this on the board, and we're going to go through this together. These are puzzles. As I said before, in balancing, some people are better at puzzles than others. But if you follow my process here, I will, you should be able to do any of these. None of these that are going to be super duper duper hard. Cool. Here's the goal of Hess's law. The goal of Hess's law is to try to get the change in enthalpy for a reaction without actually doing it. So can we predict how much heat a reaction is going to release or absorb without actually running the reaction? And it turns out we can. We can actually do that 3 different ways. This is our first of 3 ways. Okay, you're going to get another way tonight, and maybe the other way tonight as well. And then again, 1 and 2, we really, really, really get into it. So there are 3 ways to predict the heat that a chemical reaction will give off without actually doing it. And Hess's law is like the puzzle method. It's our first method. And this method is what I think is the most fun because I like puzzles. Okay, so here's how this works. We are going to be given a couple reactions that we can combine and get everything to cancel out that we don't want and be left with the overall reaction. Now, because the heat energy is, or enthalpy, is what is called a state function, which you don't have to know what that is, okay? But because it's this thing called a state function, what that means is that the reaction doesn't, that the change in enthalpy does not depend on how many steps it takes to get there. It's just, as long as, it doesn't matter if it takes 1 step or 20 steps, as long as what goes in and what comes out are the same and everything else cancels out, then you can do this method where you can combine reactions and make it work. So what we're going to do here is we have two reactions that somebody has already done, and we know the enthalpies for. We know this first one, 2 NOs goes to N2 plus O2. We know that releases 180 kilojoules per mole of energy. And we know O2 plus 2NO makes 2NO2 that also releases 112 kilojoules per mole of energy. Okay, so here's how I like to do these problems. I like to take the reaction that we want. This is the reaction we want. I like to work my way across that reaction, okay? And I like to, take care of each thing from left to right. Now, there is only one tip I can give you for Hess's law. The rest of this is just puzzle skills. Okay, the only tip I can give you for Hess's law is work your way across the reaction that you want from left to right. But if something is in more than one reaction, skip it and move on. It's going to be too complicated to try. So let me show you what I mean. The first thing I need is I need an N2 on the reactant side. I need one N2 on the reactant side. So we're going to look at our known reactions, and we're going to see which one, hopefully only one, has N2 in it. And it's this first one. The first reaction has an N2 in it. But there's a problem. I need that N2 on the reactant side, and this reaction has the N2 on the product side. So what we need to do is flip the first reaction. But remember, what do you do when you flip a reaction? When you flip a reaction, you change the sign. So we're going to flip reaction 1. It's going to become N2 plus O2 goes to 2NO. And since we flipped it, the change in enthalpy is no longer a negative 180. It's now a positive 180 kilojoules. And now that reaction is done. You will never use a reaction more than once. So we're done with that reaction. That reaction is done. Next up is O2. But here's the problem. O2 is in more than one reaction. So whenever something is in more than one of the given reactions, I suggest you skip it. Now, this one would be kind of easy to figure out, but I would suggest you skip it and move on. And it's going to work out in the end. It always works out in the end. Don't worry. So we're going to move on to the two NO2s. So we're going to look, and the second reaction has NO2. It has two of them, and they're on the product side. It is perfect just the way it is. It's on the right side. I got the right number of them. I don't need to multiply anything. So we're just going to reuse reaction 2 exactly the way it is. So O2 plus 2NO goes to 2NO2. I didn't do anything to the reaction, so the enthalpy is still a negative 112 kilojoules. And here's the fun part. This is the fun part. This is like this is where you get to cross stuff out. And this is like, if you ever seen Good Will Hunting, fantastic movie. Oh my goodness, right? Matt Damon, love Matt Damon. Robin Williams, Ben Affleck, Minnie Driver, that dude from Andor and Star Wars, whose name I don't remember, the Swedish guy. That's what an amazing movie. Anyway, although I'm reading a book right now called Bad Therapy. And they talked about, I was reading it last night, and they were talking about how it's just such a misconception that, the Matt Damon's character, Good Will Hunting, needed to have that breakthrough and deal with his past before he could move on. And I don't know, he's dead. But anyway, I digress. This, to me, there's a scene in Good Will Hunting where Matt Damon and the Swedish professor, whose name I don't know, they're at the board and they're solving a problem, and then they just pop, start crossing stuff out, right? This is that moment. This is your Good Will Hunting moment. This is where you get to cross crap out. Okay, now this one doesn't have a lot to cross out, so it's not like a super duper Good Will Hunting moment. But here's what you're looking for, folks. You're looking for something that's on the product side and on the reactant side. Okay, and the two NOs are on the product side and the reactant side. We're making two NOs, but then we consume them, so it's like they were never there. We call that a reaction intermediate. Okay, so they cancel out. Now you got to be careful. The O2s do not cancel out. Why do they not cancel out? They're on the same side. And if the O2s are on the same side, then they actually add together. So what are we left with here? We're left with N2 plus 2 O2s goes to 2 NO2s. And now we got to add this up. The change in enthalpy, 180 minus 112. So 180 minus 112. That's a positive 68 kilojoules. That's my change in enthalpy. We did it, folks. What did we just accomplish? We were able to figure out the change in enthalpy for this synthesis reaction without actually doing it. by taking reactions that had already been done, combining them in such a fashion that everything cancels out except for the reaction we want, then we can add up the enthalpies and get the enthalpy for the new reaction. It's amazing. What we've determined is that this reaction is actually an endothermic reaction. If you wanted to take an N2 and combine it with if you wanted to take an N2 and combine it with two O2s directly to make two NO2s, that would require 68 kilojoules of energy. You got to put 68 kilojoules of energy in there to get that bad boy. So that's Hess's law, folks. Okay, you just work your way across the reaction from left to right. If something is in more than one reaction, skip it, and hopefully it all works out in the end. So pretty awesome.